Okay, here we have the notes for section P5, solving equations graphically, numerically, and algebraically. So the first way we'll take is graphically. So we're going to solve the equation 2x squared minus 3x minus 2 equals 0 graphically. So first I'm going to draw on some axes here. So if you are solving graphically, you are looking for the values where the graph crosses the x-axis. So to do this graphically, I'm going to need a t-table. So we'll do -2, -1, 0, 1, 2, and we'll see if that gets us enough values to actually answer the equation. So if x is -2, I'm going to plug -2 in for all of my x's. So that becomes 2 times -2 squared minus 3 times -2 minus 2. So that gives me, oh, that's a really large number. That's 12. I'm going to go back through and plug 1 in, or -1 in, sorry. -1 squared minus 3 times -1 minus 2. So that is 3. If I plug 0 in, that's -2. If I plug 1 in, get -3. And if I plug 2 in, I bet I'm going to get 12 again, because I can see a pattern. Oops. Oh, nope. Did I put that right? Yeah, 0. Okay, so -1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one's off the top of the graph. -1, 3 would be right there. 0, -2 would be down there. 1, -3 would be right there. 2, 0 would be right there. So got a value there, and there's a value there. So those would approximately be the solutions to the graph. So x equals about -0.5, and x equals 2 would be my solutions. All right, so here you have the zero factor property, which just means if you multiply two values together and the product is 0, one of the two of those things must also be 0, because 0 times something is 0. Down here you've got a quadratic, so a quadratic always has that form, ax squared plus bx plus c is equal to 0. So this example 1 up here is an example of a quadratic. Now the one thing is that the value for a can't be 0, because then you don't have an x squared, and that's what makes it a quadratic. Okay, so we're going to solve this guy algebraically. So 2x minus 1 squared is equal to 9. So the first thing I need to do is get rid of the squared. So to do that, you take square roots. So you get 2x minus 1 is equal to 3. Now that, though, is not the whole story, because 2x minus 1 could also be equal to -3. The reason is, remember, a square root is what two numbers multiply to make positive 9. So 3 times 3 is 9, but so is -3 times -3. And then these two questions solve independently, so add the 1 across gives me 4, divide by 2 gives me 2. And over here, 2x is equal to -2, add the 1 across, x is equal to -1. So those are my two solutions. If you check, if you plug them back in, you should get the solution. So if I plug 2 in, that becomes 4 minus 1 is 3, 3 squared is 9, so on and so forth. All right, so example 3, we're going to do by completing the square. So that uses this formula. So when you complete the square, the first thing that you need to do is move the constant term to the right-hand side. And then you divide everything by that coefficient. So this becomes x squared minus 5x is equal to -17 over 4. Now on the left, we're going to add this value here that's equal to b divided by 2 squared. So there's my value for b. So I'm going to take 5 divided by 2, so that's 5 halves, and I'm going to square it, and that is 25 over 4. And I also have to add it over here on the right, because what you do to one side, you must do to the other. So this becomes x squared minus 5x plus 25 over 4. Is equal to 8, so this is going to be 8 fourths, so that's 2. Now this is a perfect square if you look at factors as x, and then it's b over 2, so minus 5 halves squared is equal to 2. Now this one from here solves exactly like the one up above. I take the square root of both sides, so x minus 5 over 2 is equal to plus or minus the square root of 2. Now I'm being kind of lazy here. 2 doesn't have a square root, so I'm going to leave it as root 2. And I can, since I'm doing just that, I can leave the plus or minus in front, which is where here that's the plus and minus version. And then the last thing is I need to move that across. So x equals positive 5/2 plus or minus the square root of 2. And that is your solution. You do not go any farther. The other way to solve a quadratic is just by using the quadratic formula, which uses that formula so you plug the values in and numbers come out at the end. The quadratic formula is nice in that it will always work. So we're going to solve this guy using the quadratic. So to use the quadratic, the first thing you need to do is move everything to one side. So for this problem, a is 3, b is -6, and c is -5. So for the quadratic, it is negative b, so it's going to become positive 6 because it's a negative, square root of b squared minus 4 times a times c all over 2a. So that's 6 plus or minus the square root of 36 plus, that's going to be 60, I believe, over 6. So that's 6 plus or minus the square root of 96 over 6. Now 96 is not a perfect square, so I need to do a factor tree for it. We'll do that guy over here to save myself some room. So 96 is 2 and 48. 48 is 2 and 24. 24 is 2 and 12. 12 is 2 and 6. And 6 is 2 and 3. So there's a pair of 2s. There's a pair of 2s. So a 2 and a 2 are going to come out, so that's 4. And then, there on the screen, those two numbers multiply back together, giving me 6 all over 6. Now, 6 and 4 and 6 are all even numbers, so I can divide everything by 2. So 3 plus or minus 2 square root 6 over 3. And that's as far as you can go. These 3's do not reduce because they can't cancel anything out of that 2. So solving a quadratic, you have these methods. You can factor it. You can extract square roots, which is what we did in the second example. Complete the square, which is example 3, and quadratic is example 4. All right, so here we have example 5, a cubic. So graphically, so once again, we are going to just sketch the graph. So a t-table is needed. So -3, -2, -1, 0, 1, 2, 3. And we're going to see where it crosses the x-axis. So I'll start with -3. So where are we? -3 cubed minus, oops. Oh, that value's going to be off the graph. That's -25. So if we do 2, we get 5. If we plug 2 in, make sure here, -2 in, sorry, -2 cubed minus -2 minus 1. Nope, -7. If I plug -1 in, -1 cubed minus -1 minus 1. So that's -1. When it's 0, it's -1. When it's 1, it's -1. When it's 2, it's 8 minus 2 minus 1, so that's 5. And when it's 3, that's 27 minus 3 minus 1, that's 23. So -2, 1, 2, 3, 4, 5, 6, 7. -1, -1, 0, -1, 1, -1, 2, 1, 2, 3, 4, 5. And 323, so something like that. Oops, that's in the wrong. That's totally in the wrong place. That's just -7. 1, 2, 3, 4, 5, 6, 7. That point should be down there, so it should look like this. It goes across and down. So you have a solution somewhere in there. So that's at about, I don't know, 1.5. So when you solve graphically, your answer is going to be an approximation because you're going to have to read the value off of the graph. All right, so using a table, so that's actually kind of what I did over here. So here's my table of values. So I'm looking for where it switches from a negative y value to a positive y value. So that happens somewhere in there. So somewhere between 1 and 2, 1.5 is a good example. So we'll just put a note here. See t-table on example 5. So you're looking for where the sign switches from negative to positive or the other way around. All right, so here, by finding intersections, solve the equations like this, if it lies on both graphs. There's another way to do it, and that's actually just to solve the equation, which we'll do this way. So 2x minus 1 is equal to 6, and then 2x minus 1, since the absolute value, also has to equal negative 6, because the absolute value function equals a positive and the negative value. So if I add the 1 across, I get 7, which makes this 7/2. If I add the 1 across here, I get negative 5, which makes this negative 5/2. And that's the end of the section.